Good morning, this is Miss Backfish, and I am here to talk to you about what I'm calling working with six trig functions. And let me explain what I mean by what I'm calling. For my dual enrollment students, this is lesson 4.4, and where we are, how to come up with the unit circle and how to use the unit circle. So if you haven't already figured out, if you don't understand where this comes from, or what it means, or how to create it, I would advise first watching my video called Building the Unit Circle. But once we have established this, pretty much this section is just working with the six trig functions in several different ways. It's just different types of problems, things that you can be asked to do. So that's pretty much all we're going to do, is we're just going to look at different types of problems working with trig functions. And the first one looks like this. Find the exact value of each of the six trigonometric functions of theta given a point on the terminal side of an angle theta. Now, the key here is that the points you're given are not any of these points. They're not the unit circle points. Okay, if you were given these points, then you could say, oh, okay, I know that the x-coordinate is the cosine and the y-coordinate is the sine, and I know these other relationships like our reciprocal relationships and our quotient identities. But here, it's more like you're given a point like 3, -8. A point that does not look like anything you see on the unit circle. So what you want to do is you want to sketch this point. You want to go ahead and figure out where would I graph that. So that's to the right and down. So really I'm in the fourth quadrant, 3, -8. Let's move over here a little bit. Just a rough sketch. Connect it back to the origin. And then from your point, go to the x-axis at the closest location, and that creates your right triangle. So what you're doing here is you're creating a right triangle given this point. Now, from here, you're pretty much going to use SOHCAHTOA. You're going to use the definitions of sine, cosine, and tangent, and the relationships we know between those trig functions and cosecant, secant, and cotangent. And I'm going to say, okay, this is 3 indicates this side right here. And the -8 indicates how far I'm going down. All right, so then I need to find the hypotenuse. And the way I'm going to find the hypotenuse is the Pythagorean Theorem. So whether it's the hypotenuse or something else you're finding, one of the first things you want to do with this is find the missing side of your right triangle. All right, make sure when you square -8, if you're using a calculator, that you remember to put the negative inside what you're squaring. Don't get a -64. So this gives me 73. So that means this. Now, when you're setting it up like this, the hypotenuse is never, ever, ever negative. It's always positive. So if you have negatives, they will come in your horizontal or vertical components. Okay, the x or the y. So now that I know all the sides, I'm ready to use these definitions and what I know about their relationships to other trig functions to find all my values. So I generally like to do it in a certain order. And what I do is I do this, and then out here to the right of this, I'll do the reciprocal. So next to sine, I'll do cosecant. Next to cosine, I'll do secant. And next to tan, I'll do cotan. And that just sort of helps me keep straight what goes together. So the sine, and here's the theta, it's always the angle closest to the origin, is opposite over hypotenuse. So that's -8/√73. Now we have to rationalize that, but before I rationalize it, I'm going to go ahead and do the cosecant because it's easier to flip this than to wait and rationalize it and then flip it, because then I'd have to rationalize it again. So cosecant is the reciprocal of sine, so this is going to be -√73/8. And rationalized, it looks like this. So there's my sine and my cosecant. The cosine of theta is adjacent over opposite. So same thing happens here. I'll have to rationalize, but let me wait and figure out the secant first. And then finally, the tangent is the opposite over the adjacent, which there's no need to rationalize, which is nice. Remember that when a function is negative or positive, whichever one, its reciprocal is the same sign. Its reciprocal would also be negative or positive. So this is what you're doing for each one of these. So you actually just graph the point, and that tells you what quadrant you're in. That shows you what quadrant you need to be in. Draw your right triangle. The right triangle always needs to have one side touching the x-axis. So from your point, you always go to the x-axis, and that's where your horizontal component is. And it pretty much works the same for every problem with these. Okay, so if you see values that don't seem to be unit circle values, and that's very often the first clue, is you're humming along using the unit circle, and then you see a problem like this, and you're like, wait, I do not see 3, -8. Well, that means you're going to draw the triangle. All right, next up, evaluate the trigonometric function at the quadrantal angle, or state that the expression is undefined. I'm not sure that I had ever heard the term quadrantal angle until maybe I was in college, and I don't know that I've heard it since until this textbook. It's not a common phrase, but basically what it means is when we think about the quadrants, first, second, third, fourth, and that's not really relevant here, but just a reminder. The quadrantal angles are the angles at the boundaries of each of the quadrants. So in other words, 0, and in radians, this is pi over 2, pi, 3 pi over 2. And very often we're dealing with radians. That would be 90 degrees, 180 degrees, 270 degrees. So specifically, we're going to be asked about those angles when we say at the quadrantal angle. Or state that the expression is undefined. So let's talk about why this expression might be undefined. And we can, again, reference the unit circle here. But remember, the whole reason the unit circle is called the unit circle is because the radius is 1 unit. So if I go up, I'm at 0, 1. If I go to the right, I'm at 1, 0, and so on. All right, so this is the cosine and then the sine, right? So if the cosine is 0, if I flip it over to talk about the secant, then I have 0 in the denominator, which would be undefined. If the sine is 0, and I flip it over to talk about the cosecant, then again, undefined. So for instance, if you have something like, let's do cotangent of pi. Here's pi. Remember that tangent, this is kind of what goes through my head when I'm doing cotangent. Tangent is the sine over the cosine. That's one of my quotient rules or quotient identities. So cotan is the cosine over the sine. Cosine is the first coordinate. Sine is the second coordinate. This is undefined. Why? Because it has a 0 denominator. We can't have that. Remember though, if a fraction has a 0 in the numerator, that just means the value is 0. Let's look at, how about secant of 3 pi over 2. Okay, the secant is the reciprocal of the cosine. The cosine is 0. What's the reciprocal of 0? That would be 1 over 0. So again, it's undefined. What about the cosecant of 3 pi over 2? Cosecant, sorry about that. Now that is the reciprocal of the sine. If the sine is -1, the reciprocal of that is still -1. If you take a -1, which as a fraction is over 1, and we flip it, we get -1. I like to put my negative up on top. You can put your negative out front. We usually do not put the negative in the denominator. But just remember, if you have a negative either in the numerator or in the denominator, that means the whole fraction is negative. So that's what's meant by quadrantal angle. Honestly, they really don't even need to say that. because you're going to evaluate the trigonometric function at whatever angle they give you. So it's just a little bit of a vocab lesson in the middle of the question. Moving on. Let theta be an angle in standard position. Name the quadrant in which theta lies. Okay, so what we're being asked to do here is to look at something that we very often use, but very often do not look at explicitly. So it's actually kind of nice that we're asked to do this explicitly because it gives us a second to stop and look directly at it, as opposed to looking at it in the context of doing something else. Okay, so we're going to think about what's going on in each of the quadrants. In the first quadrant, everything's positive, right? So that means my cosine is positive. My sine is positive. And remember that the tangent is the sine over the cosine. So if they're both positive, the tangent is positive. Now, for a fraction to be positive, the numerator and the denominator have to have the same sign. In other words, positive over a positive makes positive, right here. Or negative over a negative makes positive. So the other place the tangent would be positive is actually in the third quadrant. Because, I'm sorry, that's a 0. Because in the third quadrant, the cosine and the sine both have the same sign, which is negative. The x value is negative, the y value is negative. And so if I put one on top of the other, then I get a positive, and that's why the tan is positive in the third quadrant. Now, in the second and fourth quadrants, the sine and cosine have opposite signs. One of them's positive, one of them's negative. And I always think of it like, you know, I've been doing this for many years, but I still tend to think of it as, I think, over, up, left, up. Left is negative in terms of x. So cosine is negative in this quadrant. Up is positive for y. So sine is positive in this quadrant. And the tan, since we're mixing positive and negative, whoops, I'm having problems here. I should be using a pencil, is negative. The tan is negative in the second quadrant and also in the fourth. Finally, fourth quadrant, we're going right and down. So positive, then negative. So cosine is positive. Sine is negative. And the tan, since it's mixing positive and negative, is also negative. So what you're going to be told, questions like this very often will say something like, that's what you're given. And you're supposed to name the quadrant in which theta lies. Okay, so I need to go to a quadrant where tan is positive. That would be 1 or 3. And the cosine is negative. Well, it's positive right here. So that's quadrant 3. So that's what you're doing on these. And really, they're getting us ready for other questions that ask this in a sort of more implicit way. In other words, we have to figure this out in order to figure out what the problem is asking, but it's not specifically asking me what quadrant. Now, very often what those will look like is problems a little bit like this, where maybe something is told to me in such a way that I need to draw a triangle, but I'm not given the coordinates, but I need to know what quadrant to draw my triangle in. Okay, so let's go ahead and look at something else that uses that. Okay, so here's a problem. I need to know what quadrant to put my triangle in, but it tells me, so that's nice. All right, it says the cosine of theta is negative 9 over 41. Well, there's two different places, two different quadrants in which cosine is negative. So that's why they have to tell me quadrant 2. So notice these are not unit circle values. There's no 9 and 41 on the unit circle. So that's another reason I know I need to draw a triangle. So when you've got a situation like this, just go ahead and draw a segment that just goes out somewhere in the middle of that quadrant. And then from the end of that segment, go back to the x-axis, and there's your right triangle. With a really kind of funky right triangle symbol. Sorry about that. Okay, cosine is adjacent over hypotenuse, still using SOHCAHTOA. So my adjacent goes here, and my hypotenuse goes here. Now, let's talk about signs. This fraction is negative. It could have been told to me instead of the way I wrote it, and I just tend to write it, like I said, in the numerator. I could have put the negative out front. So sometimes you really do need to think about, even if it was written like this, you need to think about where's the negative. The hypotenuse, we already said this, the hypotenuse is never going to be negative when you draw these. Since it's negative, that means one of these two has to be negative. Well, think about where it is. Second quadrant, negative, positive. So always make sure to do that, to think about where it is and go, okay, this would be negative. And whatever I get for here is going to be positive because I'm going up from the x-axis. So Pythagorean Theorem again. 9 squared plus something else squared equals 41 squared. So I'm going to subtract 41 squared minus 9 squared, and then take the square root of that number, and I get 40. So this is positive 40. So take the time to think about your signs and make sure you got the right signs in the right places. Now I can go ahead and find all the rest of my trig functions. And like I said, I like to be pretty consistent in doing them in the same order. So sine is opposite. Here's theta. Theta is always closest to the origin, opposite over hypotenuse. So there's my sine. That makes my cosecant 41 over 40, the reciprocal. The cosine we already knew was negative 9 over 41. That makes the secant negative 41 over 9. And the tan is positive 40 over negative 9, but I'm not going to put a negative in the denominator, so I'm just going to call that negative 49ths, meaning that the cotan is negative 9/40ths. And those are my answers. Okay, we're going to do a couple more of these because there's different ways that you can be told this. All right, this time we were told flat out we're in quadrant 2. But just like we were saying, what quadrant are we in? Sometimes we're being asked directly, what quadrant are we in? Sometimes we're told in a more kind of oblique way. Like for instance, let's say we are told that tan of theta is 5/2 and secant theta less than 0. Now what are they telling me? They're telling me the secant is negative. My thought process, anytime I'm talking about secant or cosecant, is that goes with the, and in this case, secant goes with the cosine. So if they're telling me the secant is negative, that's like telling me the cosine is negative. So where's the cosine negative? Over here on the left. That's where my x value would be negative. So it's either quadrant 2 or quadrant 3. They gave me the tangent value, and they said the tangent is positive 5/2. That means it has to be the quadrant out of these two which has positive tan. Remember, we said that tan is positive in the first quadrant or in the third quadrant because that's where the sine and cosine both have the same sign in terms of positive and negative. So it has to be the third quadrant. So that means I'm going to draw a third quadrant triangle. Excuse me. Tangent is opposite over adjacent. Now think about the signs. In the third quadrant, everything is negative in terms of my x and y. So that's my horizontal component and my vertical component. Hypotenuse is never going to be negative. But we're going to use negative 2 squared plus negative 5 squared. And we know that when we square a number, we get a positive. If you type it in your calculator, don't psych yourself out by forgetting to include the negative inside what's being squared. Both of those, when I square them, I'm going to get a positive number. So in other words, 4 plus 25, which is 29. So the hypotenuse here is square root of 29. And now I'm ready to do what I did here. Just sine is opposite over hypotenuse. And this is another case where I'm going to have to rationalize. So I'm going to go ahead and do it without rationalizing first so that I can flip these. for my reciprocals without having to rationalize twice. So in other words, this is cosecant. Oh, I shouldn't have put that comma there, should I? Cosecant is negative root 29 over 5. Secant is negative root 29 over 2. And cotangent is 2/5. The reason I shouldn't have put my comma there is because I need to rationalize this. So this is that. And this would be that. All right, last problem of this type. And it's really just one more way to tell me what quadrant I'm in, is this. This is just a fancy way of saying I'm in the fourth quadrant. Okay, because here is 270, here is 360. We're saying that we're between them. Nope, can't see it. There we go. It could also be said this way. 3 pi over 2 is less than theta, which is less than 2 pi. Same exact thing. It's just a way of saying I'm in the fourth quadrant. So let's draw our triangle in the fourth quadrant. Now, secant goes with what? Secant goes with cosine. So if the secant is 12, that's like telling me the cosine is 1/12. So that's 1 for adjacent and 12 for hypotenuse. Adjacent over hypotenuse is what I've got here. In the fourth quadrant, my x value is positive, and then we have a y value that's negative. So I'm going to go ahead and use Pythagorean Theorem. 12 squared is 144 minus 1. This is going to be root 143, but it's also going to be negative. And now I have my triangle, and now I can go ahead and do sine, cosine, tangent, etc. All right? So we're not going to go all the way through those. It pretty much works exactly the same way it did on the last couple of examples. Okay, so another type of problem that's in this section is, and it's honestly, it's a little weird to me that it's in this section. It says find the reference angle for each value of theta. And it gives me something like this. Now, to me, if we are at this point and we've already talked about the unit circle, then we've already talked about reference angles. Because when we're talking about the unit circle, we talk about how this angle, all the ones marked in pink, they all have the same reference angle. They're all 30 degrees above or below the x-axis. So to me, that's kind of old news at this point, but that's okay. We're being asked about it. So the reference angle is basically how far are you, what is your angle between your terminal side and the x-axis for your quadrant, whatever quadrant you're in. Okay, in other words, here, how far above or below the x-axis is your terminal side. So if you're in the first quadrant, your reference angle is exactly what your angle is. In the second quadrant, it's 180 or pi minus your angle, because you are less than that. You have turned starting over here and you're not quite to 180 yet. So the question is, how much are you lacking to get to 180? How much less than 180 are you? Now, when you're down here, it's how much bigger than 180 are you? Like, for instance, if it's 210 degrees, my reference angle would be 210 minus 180, which is 30. And over here, you're almost all the way back around to 360 or 2 pi. So it's how far do you have left to go to get there would be your reference angle. So 360 or 2 pi minus wherever you are. So 257, remember this is 270, it's somewhere like here. So my reference angle would be right there. So we're in degrees, so I'm going to subtract 257 minus 180 to figure out how many degrees past 180 I have rotated. And that would be 77. Okay. Another problem like that. Let's go ahead and do that to differentiate. Theta equals 9 pi over 5. Okay. Now, my first thought on this is just to make sure it isn't greater than 1 rotation around. Because if it is, if it's more than all the way around the circle once, then I would have to get a coterminal angle. In other words, I would have to go ahead and sort of walk back to where I am between 0 and 2 pi. And this is something I talk about more in that building the unit circle video. Actually, another one before that, I think. So when I think about 2 pi, if I'm thinking about fifths, 2 pi over 1 is 10 pi over 5, because 10 divided by 5 is 2. So this is less than 10 pi, so it is less than 1 rotation around, so that's nice. But it's not much less, so it's in the 4th quadrant. Okay, so all the way around would be 10 pi over 5. So if the question is, how far am I from there? I'm going to subtract 10 pi over 5 minus 9 pi over 5, which is just like subtracting 10 fifths minus 9 fifths, and I get 1/5, or pi over 5. That's my reference angle. Reference angles are always positive because it's saying how many degrees or radians are you away from the x-axis. It's like distance. How far are you from this? It's kind of like absolute value. How far are you from 0? How far are you from the x-axis? All right, let's look at a couple of not as straightforward ones. Negative, okay? Negative means rotate the other way, which is instead of counterclockwise, going clockwise. So if I'm rotating clockwise, here's 90, here's 180. So we're a little bit past that. So here we are, somewhere up here. So if I want to know how much this is, then I'm asking how far it is from negative 180 to negative 192. And honestly, you could subtract either way, because if you get a negative, you just have to remember, oh, reference angles are never negative. The distance between 180, the negative 180, and negative 192 is 12 degrees. So that's my reference angle. And last but not least, just want to point this out. Sometimes, look carefully, there's no degree symbol. Sometimes you're given radians and decimals. Okay, so we're working in radians. If you see something like this, and very often it'll be a number between 0 and 6.3-ish, because remember 2 pi is 6.28, blah, 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 blah. No degree symbol. This is a radian measure. It's just expressed as a decimal. Okay, so think about where we are here. It's positive. Pi is 3.14. All right, this is half a pi. Half a pi is going to be, 1.5 something. So we're in this quadrant, and that's really what matters, is what quadrant am I in? And then we know where the closest x-axis is, and we can subtract in order to figure out how far are we away from that. So I'm subtracting 3.1415926, etc., pi, minus 2.6. And I would probably round to the hundredths. And I get 0.54. I am fine with doing a decimal on this one because the problem was given as a decimal. If we're given our problem as a decimal, we generally don't worry about being in exact form, unless it specifies that we need to. But kind of a general rule of thumb for math, period, is if they're giving you the problem, if the problem has decimals, then it's okay to give a decimal answer back. All right, and finally, this is the last type of problem in this section. And again, to me, it's a little odd to be doing this after we already know the unit circle, because some of these, the unit circle helps. But let's look at this one. Cotangent of 11 pi over 3. Well, all the way around the circle, remember, is 2 pi. In terms of thirds, that's 6 pi over 3. 6/3 is 2. So 11 pi over 3 is more than 1 time all the way around the circle. So the first thing I would do is I would find an angle that is coterminal that is less than 1 time around the circle. Meaning I would say 11 pi over 3 minus 6 pi over 3 equals, that would be 5 pi over 3. So this is going to be exactly the same as this. Coterminal means the terminal side is in the same location. 5 pi over 3, 1/3, 2/3, 3/3, 4/3. It's right here, 5/3. That's a unit circle value, okay? So I don't really understand why they're asking me to use reference angles if I have the unit circle, because I can look at it and go, okay, here are my values for sine and cosine. Let's figure out how to get cotangent from those. All right, so you can think of it in terms of reference angle, because if we're at 5 pi over 3 and all the way around is 6 pi over 3, my reference angle is pi over 3. So this is going to be the same as doing the cotan of pi over 3. But I do have to think about sine. If I'm in the fourth quadrant, cotangent is just like tangent, it's negative. So it's really the opposite sign from that. But I'd rather honestly just use the unit circle. And when I'm doing that, my first thought is, okay, 5 pi over 3, what are the coordinates of 5 pi over 3? That's 1/2, negative 3 root 2, negative square root of 3 over 2, excuse me. This is the cosine, this is the sine. Cotangent is cosine over sine. So I'm going to put this guy on top of this guy. And when we're dividing fractions like that have the same denominator, they basically end up canceling each other out. And we need to rationalize this, so I get negative root 3 over 3. And that's my answer. Okay, I hope this has been helpful to you, and I will see you next time.